time. It's one of the most fundamental parts of the human experience. We remember the past, live in the present, and plan for the future. These three sections determine how we live our lives, so much so that we don't even think about it. This is, after all, the way our universe is structured, and so for human brains that evolved in it, it is perfectly natural to see it this way. We don't really think too much about how time works, but maybe we should. By defining our terms and making sense of time, we can view it more directly, and then, perhaps more excitingly, go beyond it. There are a few different ways to visualize time, one of the most common being a timeline. This is a line on which we place events. Events are anything that occurs in our universe, such as a collision of objects, a conversation between people, a war between states, or anything else that can happen. Events have a beginning, the time in which the event starts, and a duration, the time during which the event is considered to be ongoing. We can mark events by displaying their duration on our timeline, like so. You can see this divides our timeline into three sections: the time before the event, the time during the event, and the time after the event. The time during the event is obvious enough, but how do we decide what is before and what is after? Well, on a general line, this would be entirely arbitrary, but on a timeline, these words have clear meanings relating to causality. An event can only be caused by events that are before it, and events can only cause events that occur after it. For example, say we have a timeline with an event that marks a rock falling off a cliff. If we point to some event in the future, it could not have possibly caused it, since by that point the rock already fell. The fact that the rock fell is immutable. That information about the universe cannot be changed past that point. Likewise, nothing before the event could have been caused by the rock falling, since at that point it was unknown that the rock would fall, so nothing could have been affected by it. However, an event after the rock fell, like a tree being destroyed by the falling rock, could have easily been caused by the rock falling, since it's after the event. And likewise, an event before the rock fell, such as the rock sliding down a cliff, could have caused the rock to fall off the cliff. We can formalize our intuition here by assigning numbers to the properties of our events. The start of this event, the rock falling, can be assigned the number 0, for 0 seconds. It can then be assigned the duration 2 seconds, for how long it was occurring. Then, the start of the tree being destroyed could be assigned 2 seconds, since it happened right after the previous event ended. And let's say it took 0.1 seconds to occur. We can do the same to any other events. Now, we have a way of determining whether a given event is before another. Just take the start times and see which one is smaller. Of course, our events with their durations can overlap, in which case we can't definitively say which one is before another, but we can take the starts of each event and compare those. This gives us the concept of points in time, represented by a single number. We can always directly compare these by just comparing their associated numbers. We can also test whether a given point of time occurred during a given event, by simply seeing if it's after the start and before the end. So this gives us two temporal objects: events, or line segments, which are one-dimensional and represent a process that has a start, middle, and end. These could be conversations, the life of a person, historical occurrences, etc. Then we have points, which are zero-dimensional and represent instantaneous occurrences, such as the time in which an event started or ended. Or possibly things that require a date, such as the time of the publication of a book, the signing of a treaty, or others. So what does time feel like for the actors immersed in it, such as a human or other sentient creature? Well, we all have a present, a point in time that we are operating within. Around this present are two regions, the past and the future. One of the most important things that separates these regions, other than causality, is that we have knowledge about the past, but not about the future. We might be able to extrapolate what will happen in the future, but we will never know exactly what occurs until it does. This knowledge of the past also usually degrades with time, as we forget aspects of things that occurred. We're also not just pure observers of events that occur in the future. We can take a part in them and change the outcome, but we can't do that to events in the past. Most of this should be pretty obvious if you lived in a universe at all, but the main reason I'm explaining all of this is so we have a firm understanding of what happens here before we explore somewhere a little more exotic. So far, we've been considering a single line of time and its 1 and 0-dimensional subspaces. Those are events and points respectively. But what if we were to add another axis to our timeline? Make some sort of time plane? Yeah, time plane, that sounds cool. But what does it actually, mean though? Well, remember how we needed just one number to represent a point in time? Now we need two. We have two axes, so two numbers it is. So, alright, remember that the difference between any old line and a timeline is causality, so the difference between a normal plane and our time plane should also be causality. But what does causality mean when you have two time directions? Well, it's a bit complicated. There are a few ways you could tackle this problem. If you try to extrapolate from the current known laws of physics, you get a structure where time directions can be rotated into each other, so the past could be rotated into the future, making causality a lot less intuitive. You could interpret this in the way Greg Egan does in his book Dichronauts, where the extra time dimension acts more as a spatial dimension with weird rotation rules. Now, I'm not going to be doing either of those. Instead, I'll define causality as so. Say we have a point in time A with coordinates AT, AU, and another point B with coordinates BT, BU. A being before B means that AT is less than or equal to BT, and AU is less than or equal to BU, and finally A does not equal B. Visually, this means that A is to the left of B, below B, or both. Before we continue, let's give some names to these axes for clarity. If you're familiar with four-dimensional spatial nomenclature, you'll know that the names for the two new directions are ana and kata, which are from the Greek words ana, meaning upwards, and kata, meaning downwards. So in the spirit of following convention, I'm going to coin the new words for the two new time directions from Greek as well. Prin from Greek prin, meaning before, and katopin from Greek katopin, meaning after. We'll use these two names for this axis, which are called the lateral axis, and then we'll use the familiar before and after for this axis, which are called the vertical axis. So if we then say that your current present is some point in time, then we have four different temporal regions, instead of the usual two. First is prin past. This one is the total past. This contains things that happened and can't be changed. Katopin future is the total future. This contains things that will happen and that you can't affect from your current present. Then prin future and katopin past are very different from anything that we're used to. These regions are partial futures. These contain things that have not occurred yet, but that can't be affected from your current present. However, it's possible that, if you still exist on one of these lines that neighbor these regions, you could have made a decision in the past that will affect it. Now, a question you might have is, how are these two time dimensions different? Since this is a world-building project and not a physics one, I'll describe this from the perspective of the actors in the universe. Along the lateral time axis, things generally go slower and require more resistance to occur. Meanwhile, along the vertical time axis, things are more fluid. The reason such a distinction is even necessary is because if both time axes worked in the exact same way, then the same exact events would happen in both, and so they'd be indistinguishable, basically collapsing into a single time dimension. Making them act different sort of forces different events to occur on both, therefore keeping the structure. Let's talk about events with two time dimensions. Events though take up not a one-dimensional line segment like before, but a two-dimensional area, which can be any shape. For example, let's say a rock falls like before. This is that event's area. Here I'm using a rectangle as its shape, but keep in mind this could be something else entirely. So remember how we had 3 temporal regions comprising an event before? Now we have 9. This region here is the event's total past. Anything that started the event must have occurred here. Then we have these 2 regions, whose events can affect the event while it is ongoing, but they could not have started it. Then these 2 events are where the event is in a partial future, and so it cannot be affected by what occurs there. For the most part, these past regions aren't very interesting. They're weird, for sure, not as weird as some of the future regions. So this region is during the event, but then we have these 3 regions. There's total future that's here, which is after the event is fully completed. The most interesting and important regions are these 2, the time shadows. In these regions, the event has partially terminated, in the sense that it can no longer be affected, but the outcome is still unknown. Note that the time shadows extend to the end of time, which means that for the infinite history that will occur in this small region, the outcome of the event is still unknown. As such, in something like a conversation, ideally one would want to reduce the time shadow as much as possible. It turns out that if the event is rectangle shaped, the shape that causes the minimal time shadow is a square. The proof of that is a little involved, so I won't be going over it in this video. Now that we've mentioned what both points and areas are, we can go to revisit lines. Lines are a bit weird in 2 temporal dimensions. It seems that they only represent the beginning or end of an event, analogous to what points do in 1 dimension. However, lines don't really seem to exist in isolation, unlike points in 1-dimensional time. Now that we understand the basic concepts of planar time, let's go through a possible sequence of events. Or a 2-dimensional sequence of events? A matrix of events? There's not really a word for it in English, or any other natural language that I'm aware of. Anyway, here's a time plane. Here we can see a line, which is the time during which a ball is being thrown into the air. After this, and katopin this, a few other events occur. On the vertical axis, it hits the ground and falls into a hole, and on the lateral axis, it hits the ground and stays there. Then another person goes and picks up the ball katopin after. Something important to know about 2-dimensional time is that only one thing can occur after 2 events on different time axes, so whatever happens prin and before that event must lead up to it. This also means that there's a limit on what you can do on either time axis. It has to eventually lead up to the same thing in the end. So I mentioned conversation a few moments ago. That gives me a segue into what this video is actually about. A language that the inhabitants of this universe could possibly speak, called Sei. Of course, that isn't the real name, since the real name is not pronounceable in our 3+1 dimensional spacetime. Now, let's start with the phonology. Of course, we don't have the normal phonemes that we would encounter in a mere single dimension of time. There's a whole host of things that you could do for this, one of them being creating an entirely new set of phonemes from scratch. I opted to do something a little easier, and took the phonemes that we already have, and used 2 of them for each of our 2-dimensional phonemes. Each of these sub-phonemes is called a component, and is the lateral component and the vertical component, written with a slash between them. Effectively, what occurs here is that the mouth is articulating one component in one direction, and the other component in the other direction, with the time in between those being an additive mix of the 2. So here's the phoneme chart for psi. This is a little different from the ones you might be used to. So let me explain what this even means. On the left we have the vertical component of the phoneme, and on the top we have the lateral component. A green O means that the phoneme is allowed, but a red X means that it is not. So for example, P/T is allowed because its corresponding cell has an O, but H/F isn't, since its corresponding cell has an X. Something interesting to note with this phonology is that we have a mostly 3-vowel system, or 9-vowel system since each combination thereof is a valid phoneme, but with the addition of schwa. The schwa is primarily used in order to make previously unpronounceable segments pronounceable. So for example, if I have this word, you may notice that the segments along these 2 lines have a consonant without a preceding or succeeding vowel, which makes it hard to pronounce since it's just a consonant in isolation. In order to fix this, we simply add a double schwa sound after the consonant. This is actually very common. It shows up at least once in pretty much every word, with only a few exceptions. Phonotactics for psi looks like this. Of course, we have 2 time dimensions, and so of course this is 2-dimensional as well. Here C is a constant and V is a vowel. Phonemes caterpin of another are written right of the phoneme, meanwhile phonemes after another are written above. A unique part of working in 2 time dimensions is that oftentimes you'll want to rotate words along the 2 time dimensions to save space. Now, to be technical, when I say rotate, I'm actually referring to a reflection over the diagonal, but the speakers of psi tend to think of this operation more as a rotation. Keen observers might have noticed that this phonology is not symmetric. A phoneme like P/L is allowed, but L/P isn't. This means that when a word is rotated, its phonemes undergo rotation mutation, where phonemes disallowed by the phonology are turned into allowed phonemes. This is a rather simple process, where each disallowed phoneme is mapped to a single allowed phoneme, according to this table. As far as grammar goes, psi is a mostly analytic language with some fusion of elements. Sentences can either be lateral or vertical. A lateral sentence has the next word be a word caterpin from the previous, while vertical sentences have the next word be after. Lateral sentences use words as is, while vertical sentences use rotated words. Psi's word order is fixed and looks like this, with O representing subjects, V representing verbs, S representing subjects, and A representing adjectives or adverbs. Here I'm using a pretty loose definition of adjective and adverb, because things like the locative particle or verb conjugations occupy the A space. Which, now that I've mentioned it, let's talk about verb conjugations. There's a total of 36 different verb conjugations for each subject-tense combination, listed in this table. There are 4 subjects: first person, second person, third person animate, and third person inanimate. Then there are 9 tenses: pren before, pren after, caterpin before, caterpin after, pren present, caterpin present, present past, present future, and present. Note that pren present, caterpin present, present past, and present future all imply the continuous aspect. For the other tenses, the continuous aspect can be marked manually with this word, and the perfective aspect can be marked with this. Something that's interesting is that there are sometimes 2 or 3 temporal variations of words where we usually expect 1 in our simple linear languages. For example, the word for then or next has 3 variants: caterpin present, present future, and caterpin future. These are used depending on the position of the sentence relating to the previous. There can sometimes be ambiguity on which one to use when in a complex set of sentences, and in that case, you can use any of them. So let's look at the name of the language. I've been calling it psi during this video, but that's a crude linearized approximation of what the actual name is. This is the actual name of the Conlang, which of course I can't pronounce since we unfortunately have a single time dimension in our universe. This word is broken up into 2 parts. This part is the verb for say or speak, and this part is the participle particle. So overall, the name means something like saying or speech or language. To get the linearized name, psi, I just took the bottom row of this word. Of course, you could take any row here, giving different results. Or you could slice it vertically, giving fup-i. So let's try to translate a simple phrase: I walk to school. We'll make this a lateral sentence, so sentence flow goes from pren to caterpin. And for the past tense, we'll use the pren past tense, also known as the absolute past tense. That's the bottom left of our diagram from earlier. Psi is a pro-drop language, so that means we can exclude the subject entirely, since it will be covered by the verb conjugation. The word for walk is this. Then we add the 1 pren past conjugation. Then we add school, caterpin that, and finally we add a locative particle after school. Now, the position of the word marked with a locative particle matters. If we placed it at the front of the sentence, like this, it would mean I walked at school. We must place it at the end, where it acts as a lative, I walked to school. Now, let us turn our attention to a bit of a longer phrase. This monstrosity is the beginning of one of the core myths of Psych culture. Of course, in its phonetic form, it's extremely hard to see what's even going on here. So let's go see the gloss, which is much more manageable. Let's take this sentence by sentence. Each sentence here can be pretty decently translated into a comprehensible sentence in a linear language, like English. So the subject of the sentence is star, which also means God in Sai. This is because they worship the stars in their religion. This is combined with the plural to make stars. And then we have the three animate present conjugation and the adjective above on the copula. So that structure translates to are above. The word in the object is a first person singular then with a plural, to make a first person plural. So this whole sentence translates to the stars are above us. From here, the passage branches off into two, as is common in many Sai stories because it makes optimal use of the time given. Let's go Catapin. Here we have the noun light, with a third person plural above it. Using this as an adjective signifies ownership, so this translates to their light. Next we have the verb create in the nomic aspect, an aspect which is not declined for subject. And then we have environment with all after it, which translates to all of the environment. So this whole sentence translates to their light creates all of the environment. Now, after the first phrase we looked at, we have this. Here we have a pro-adjective, which basically just means use the adjectives that were on the previous thing said, which would be this. This word translates to a whole lot of things, but for this class I chose the word character. It has a third person plural, so it's their character, and now we can resolve this pro-adjective to their, making the whole sentence their location reveals their character. Now let's go after this sentence. So this sentence is both in the future of the one before and the one prin, which means that it can rely on information from both of them. This Schwa is usually used to bring together information from its two predecessors, which could be recent predecessors, like in this case, or they could be far away, which you'd see in a longer passage. The subject of this sentence is part, followed by two, so two parts. This is in reference to the two things previously mentioned by the other two sentences, so it would be better translated to English as these two parts. Then we have determine in the nomic, so now it's these two parts determine. And then we have a subordinate clause. The way these work is that they rotate the sentence type of the entire subordinate clause, so lateral sentences become vertical and vertical sentences become lateral, and place it in the direction of the new sentence type. The .r in the gloss means rotated, since these words in the clause get, well, rotated. So we're now reading from bottom to top. So we have God in the subject, and the verb with its adverb translates to be fully. So the whole clause translates to God is fully. And as a subordinate clause, that becomes what God entirely is. Just saying God in the singular like this in Sai is often shorthand to refer to all of the gods. So the whole sentence roughly translates to these parts determine all that the gods are. This sentence synthesized information from the previous two sentences in both time directions. Each of those describe two parts, and now we mention those two parts. While we could translate this linearly by putting these sentences next to each other, it would get awkward when we try to do more than just this part. I'm not going to translate the rest of this entire phrase for the sake of time, but the gist is that this sentence builds on the sentence before it, and this sentence builds on the sentence printed. So you don't really have a good place to put the sentence if you try to translate this into a linear language. And it gets even worse when you have to insert this sentence, which builds on everything else said before it and printed. While linear translations are possible for arbitrary Sai text, they completely destroy the flow of the original, and it's pretty much impossible to reconcile. To more concretely lay out the problem, let's return to our time plane and label a few points, which will stand in for sentences. There's math coming up, so skip to this timestamp if we don't give a fuck. What we are effectively doing when we translate to a linear language is mapping each of these points onto a line. In the ideal scenario, we would want to do this in a way that preserves causality. So if an event is before or print another event, it should be before that event on our final timeline. We can model our transformation as a function from r squared, i.e. two-dimensional vectors, to r, i.e. one-dimensional vectors, or just numbers. We want to take the relation AT is less than or equal to BT, and AU is less than or equal to BU, and A does not equal B, which, remember, is what it means for a point to be before or print another point. I'm going to abbreviate that relation as A tilde B. We want to map this relation to f of A is less than f of B. In other words, f of A should be before f of B if and only if A is before or print B. We also want f to be a bijection, meaning that every event should be mapped to a unique point in the resultant timeline. This is because we can't say two sentences at the same time. So can we construct this transformation? No. Let's say we have this magical transformation f. Now take the 2 points 0, 1, which I'll call alpha, and 1, 0, which I'll call beta. Then we'll call f of alpha, alpha prime, and f of beta, beta prime. Now we know that A tilde B is true if and only if f of A is less than f of B. Therefore, not a tilde b is true if and only if f of a is greater than or equal to f of b. Since alpha tilde beta is false, i.e. alpha isn't before or prin beta, that must mean that alpha prime is greater than or equal to beta prime. But since beta tilde alpha is also false, beta isn't before or prin alpha, this must mean that beta prime is greater than or equal to alpha prime. The only way this can be true is if alpha prime equals beta prime. Since f is a bijection, this means that alpha equals beta. However, if we look at alpha and beta, they are different vectors, and so alpha does not equal beta. This is a contradiction, and it means that this magical function f does not exist. This result shows that we cannot translate psi into a linear language in a sensible way. It also sort of tells us why that's true. In a time plane, you can have events that are at different times, but not strictly before or after each other. This is impossible to do on a timeline, and so we cannot map a time plane onto a timeline while keeping its structure intact. Since we're on the topic of math, let's talk about numbers. Psi uses a bijective base 8 system. This is a system in which 0 is not written. To see how this works, let's look at something a little more familiar, base 10. Normal base 10 has digits from 0 to 9, but bijective base 10 has digits from 1 to 10. Here I'm using x to represent 10. So we count from 1 to 9, then when we get to 10 we just write x. 11 is written as usual, like 1, 1. When we get to 220, instead of writing 2, 0, we write 1x, as 1 in the tens place plus 10 in the ones place makes 20. Similarly, 100 is written 9x, 9 in the tens place and 10 in the ones place, adding up to 100. 101 is then written x1, 10 tens plus 1 1, and so on. However, instead of bijective base 10, psi uses bijective base 8, which is similar except we have digits from 1 to 8. So we have a 1's place, an 8's place, a 64's place, and so on. Psi numbers are written as a digit and then particles representing the place of that number, which are all listed here. These particles replace the Schwa/Schwa phonemes on the side of the number. As well as that, psi has a built-in way to represent two-dimensional vectors, since these are needed in everyday communication. For example, if you wanted to say something like let's meet in 2,7 hours, the way you would do this is to take the lateral component, so 2 in this case, and then interlace it with the rotated form of the vertical component, which is 7. This leads to an overlapping vowel, which you can resolve by just getting rid of the vertical component's vowel. And there you go, a single word for 2,7. You can do the same process for any two numbers. As for writing, psi is written with a logographic writing system. Every word is written with a single glyph. The language is read left to right on the lateral time axis and bottom to top on the vertical, the same way we've been writing the phonetic transcriptions. You may notice that this writing system looks pixelated. This is because most writing is done on tablets with blocks that can be placed in the down or up position. Once a full phrase is formed, this can then be printed onto a sheet of paper. Symbols may also be rotated 90 degrees clockwise to represent their rotated versions. Now, let's talk about audio. Normally, audio is a one-dimensional stream of information. The single unit of audio information is the pressure of the air at a given point in time, as units are placed in the sequence. Existing audio formats are designed with this in mind. They work to compress these one-dimensional sequences of numbers. However, we need something a little more powerful than that. Our audio is two-dimensional. We have two time dimensions from which to sample a pressure value. However, it turns out we already have a format for dealing with such two-dimensional data, images. So instead of OGG or WAV or some other audio format, the optimal pre-existing format to store audio of psi is actually PNG. Now, one may ask, why would you choose a lossless format? Audio usually takes up a lot of space, and pretty much every format for storing it is lossy. This means that information is lost in the encoding. After recording some audio, encoding it, and decoding it, the result will not be the same. For most cases, this is absolutely fine. The change is almost imperceptible. Lossy audio formats are designed to make this change imperceptible. Unfortunately, we do not have such a design for two-dimensional audio information. While we do have lossy compression for two-dimensional images, that's what JPEG does, it would most likely lead to strange artifacts on audio. Because of that, I opted to choose PNG, a lossless format for images, meaning it preserves all information. So with that said, we can now look at some waveforms of psi speech. Note that these will be crude approximations. I don't have the know-how in order to make a proper speech synthesizer that takes into account the variable lengths of different phonemes, so instead I've regularized it so that each phoneme takes the same amount of time to say. With all of that said, let's look at the waveform of the name of the language, which looks like this. And let's see the waveform of that whole phrase that we were discussing earlier. That looks like this. So finally, the last thing I'll mention before we get to the translation of the requested phrase is linear speech. This is a mode of speech in psi that sacrifices information density and brevity for clarity. Linear speech actually didn't evolve naturally. It was invented for use in situations where clarity was more important than brevity, for example when giving orders. It's used rather rarely and regular speech is very much preferred, but it is a feature of psi worth mentioning. It is also probably the most natural way to translate long phrases in a linear language into psi, which we will see shortly. It collapses subordinate phrases and other constructions by adding an insubordinate phrase particle. Then the whole phrase is rotated, and the rotated version is placed next to the non-rotated version. We can see how it improves clarity by looking at a time plane. This is a time plane of normal speech, with a rectangular shape. You can see that the time shadows here are pretty big. For something like casual speech, this is not an issue, but when giving orders or delivering important news, you ideally want these to be much smaller, so that for the greatest possible time in the future, the listener knows the whole of what's being said. A time plane of linear speech looks like this. While we gain this extra time shadow in the middle, it has a bounded size, meaning it can basically just be disregarded. Of course, in regular speech this would be filled with more words, but here we're purposefully not doing that. You can see that the time shadows on each side that extend infinitely are brought much smaller than in regular speech, so the time in the future in which the listener fully understands the thing being said is maximized. Finally, we are ready to view the translation of the requested phrase, which I'll translate into linear speech. This is rather boring and does not really show off the features of the language too well, which is why I didn't use it as an illustrative example earlier. Here's the class. Here's this inside's writing system. And here's its waveform. So that's about it. There's still so much that I didn't cover on two-dimensional time itself, and it's really crazy the stuff that occurs with two time dimensions that's utterly alien to human comprehension. At some point I'm going to make a follow-up video covering more of that. For Psi, there's a lot more word forms and other things I didn't fully cover here, but this video got the gist of it. In the description of this video you'll find a text project I used to create it, as well as a GitHub repository containing a program I used for various tasks while creating Psi, a spreadsheet containing the documentation for the language, and a script for this video. If you like this video, your opinion is wrong, you dumbass. This video is complete fucking dog shit. Go to hell. Your opinion is so bad that you probably deserve it. Maybe even multiple fucking eternities of suffering for you. Fuck you.